Welcome you now in day 2. So day 2, the lectures are scheduled in the first half. We have 2 lectures, and after the lunch we have another session. Okay, you already know the times. So I'm now going to hand over the stage and the podium to our Professor Glatzel. Professor Glatzel, now the students are yours.
Thank you very much. Good morning, everybody, and welcome back to the theory of stellar pulsations. Yesterday we have started to collect the basic physics and the basic physical principles which govern stellar pulsations, and we have started with considering the mechanics of a flow. So in other words, we have tried to collect or to derive some of the basic physical equations which describe fluid mechanics. The star behaves like a gas, and therefore its motion is controlled by the equations of fluid mechanics. We have started then with the mass conservation, and we arrived at the equivalent of the mass conservation, which is the continuity equation, either in the Eulerian formulation or in the Lagrangian formulation. The next law of conservation was the law of conservation of momentum. We have considered the change of momentum and applied Newton's law, and in the end we ended up with either the Euler or the Navier-Stokes equation as the equation of motion. In the next, for the rest of the lecture, we will not deal with Navier-Stokes equation. We will deal with Euler equation. So we drop all the viscosity effects and all the shear stress effects which may occur in a fluid. Once we consider viscous flows, then we have to take Navier-Stokes equations and consider viscous stress within our configuration. Well, the next equation we want to derive, or which we want to look at, is, of course, after we have the mass conservation and the equation of motion, we need an energy equation, and that's what we were about to derive or to consider in the last minutes of last lecture. And to prepare for the energy equation, we considered the change of the change with time of the kinetic energy. It is derived by simply multiplying the equation of motion in the usual way with a velocity vector, and then it's particularly obvious in the Lagrangian formulation. Then we have a term which goes with v times dv by dt, which is d by dt times 1/2 v squared, which is the kinetic energy. So the first consequence we did within the Lagrangian formulation, we multiplied the acceleration with the velocity vector, which is then the derivative of the kinetic energy, and we convinced ourselves, once we integrate this equation over the volume, that it represents the work done by the volume or the external forces plus the work done by the surface forces plus one term left, which we will discuss in a moment. So this is the change of the kinetic energy derived from the equations of motion, which is given by the work done first by the volume forces and the work done by the surface forces. Now, as a next step, this was a preparatory step for considering the energy balance. The total energy contained in our system is not only made up by the kinetic energy, it also contains the internal energy. And now the thermodynamics of the system comes into play. which in pure mechanics is not present, but if we consider a continuous flow, if we consider a gas, then a gas does also contain some internal energy, and then the thermodynamics of the gas or the fluid, if you consider a fluid, comes into play. So there is not only kinetic energy, not only mechanical energy, but there is also internal energy, and we write the internal energy as an integral over the volume of the energy density, the kinetic energy density, which is written as the density, the mass density times the specific internal energy, which is the energy per mass, related to the mass. So U is the internal energy per mass, and the total internal energy is then given by this integral over the density times specific internal energy over the volume. Okay, these are the two forms of energies contained in our gas, and we would like to know how this energy changes with time. Okay, so this energy changes in time because there is work done by volume forces. We distinguish between these two sorts of forces, volume forces, for instance gravity or magnetic fields. These are volume forces, and the work done by the surface forces. These are forces which act on the surface of a mass element. If we consider a mass element, then we can have forces which operate on the surface of this element. So these have to be distinguished from the external or volume forces because they act on surfaces, the other forces acts on the volume. Okay, now consider situation on Earth, a terrestrial situation. You have a diesel engine, or you have an aircraft engine. There is heat put into the gas because you have combustion in an aircraft engine, or you want to move your truck with a diesel engine. Then you have energy generation, external or chemically generated energy, which puts additional energy into the gas. The situation is similar in a star, but it's not combustion which is happening there, but it's nuclear energy generation, which can provide additional energy and which needs to be considered once we consider the energy balance. So we have to specify an energy generation. For instance, in the astrophysical context, it's the nuclear energy generation, and we design or we denote the specific energy generation. That means the energy generation per mass with epsilon. So this is the specific energy generation, energy per time and mass generated within our gas. Another effect that occurs in any real situation, that we have heat fluxes. Heat fluxes means a heat flux is a vector which goes into your mass element through the surface of the mass element. So we have a heat flux which enters, or a part of the heat flux enters the mass element, and some of the heat flux goes out of the element. If the incoming heat flux per surface area is bigger than the outgoing flux, then energy is deposited in our mass element. In the opposite case, energy is taken out of our mass element, and that, of course, in the energy balance has to be accounted for. So we have to consider that there is a heat flux, and this heat flux may deposit or take out energy of our mass element. So if we consider the energy balance, this means the change of kinetic energy plus internal energy, then we need to take into account all these effects. The work done by the volume forces, work done by the surface forces, energy generation possibly, and heat transport might lead to a change, or might be needed to account for a correct energy balance. Okay, so let us write down what all these terms. Well, this is the change of the total energy composed of the kinetic energy and the internal energy change with time in the Lagrangian sense. change of energy in our mass element. Okay, so the first term is the work done by the volume forces. We have convinced ourselves in the previous lecture that this is the term which accounts for the work done by the volume forces. And this here is the work done by the surface forces. It's pressure times velocity times the surface element. So this has to be integrated over the surface. These are surface forces, and therefore they have to be integrated over the surface of our mass element. And then we have the energy generation, which is accounted for by the energy generation rate, specific energy generation rate. If we multiply it with the density, we get the energy per volume and time which is generated, and its integral over the volume will be the energy which is deposited through the energy generation. In astrophysics, it's the nuclear energy generation, and we need to account for the flux, the amount of energy which is deposited or taken out by the heat flux. So we have to integrate the flux over the surface of our mass element, and this will be the flux or the contribution which will either take out or put in energy from the heat flux. And this again is an integral over the surface of the mass element, similar to the surface force, the work done by the surface forces. Okay, now we already saw what we can express here the change of the kinetic energy with time. We derived that term from the equation of motion, and we saw, well, this is the change of kinetic energy. It's given by the work of the the volume forces and the surface forces, and one term left. So we replace in our energy balance, we replace this term by the expression on the right hand side, and what we see that these terms will cancel with the terms which we already wrote down. Okay, so what is left here? We replace the change of kinetic energy on the left hand side. We are left with a change of the internal energy, which is the remaining term from the change of kinetic energy. These terms are already present in the change of the kinetic energy, so they will cancel, but there is the one term which is left, which some of you asked already before. This is a volume integral over the pressure times the divergence of velocity integrated over the volume. And then these two terms are left which need to be taken into account. This is the energy generation, which corresponds to this term, and we have transformed this term from a surface integral into a volume integral. So this is the integral over the surface of the flux is the volume integral of the divergence of the flux over the volume. Okay, now we are left with this equation. And since the volume or the mass element we consider is arbitrary, we can take off the integral and we can say, well, then since the volume is arbitrary, it means that d by dt, rho du by dt, we use the fact that the Lagrangian time derivative of an integral over an integrand, which is written rho times some quantity, is rho times du by dt. This was a consequence of mass conservation, and then we end up with the following equation. Oops. I have some difficulty in where is okay, so we are left with this equation, rho du by dt. Well, maybe I have to write it down. we made use of the fact that d by dt integral rho u dv is equal to integral rho du by dt dv. This is a consequence of Reynolds transport theorem and the mass conservation which is needed that we can put the Lagrangian time derivative from outside the integral to the second part of the integrand. Okay, so we have rho times du by dt is minus p times the divergence of velocity field plus rho times the energy generation minus the divergence of the flux. So what you see here on the right hand side, these two terms, this is the energy put into or taken out of the system by energy generation and the divergence of the heat flux. So this is usually or might be regarded as the heat which is transferred into or taken out of the system. And the rest of it, so this is in terms of thermodynamics, it's the dq, it's usually denoted by dq, the heat change of the heat content of your mass element. And what is the right hand side? This is the change of the internal energy. And what's that? P times the divergence of V. Pardon? It's work done. How do you see that divergence of V has to do with the PdV work in a thermodynamical sense? Well, we have d rho by dt. If you take the Lagrangian form, d rho by dt, we had this before, d rho by dt plus rho times divergence of V, or divergence V, is 0. So the divergence of the velocity field in the Lagrangian sense is maybe expressed by d rho by dt, or 1 over rho by dt. Divergence of V is minus 1 over rho times d rho by dt. And rho, if you keep the mass fixed in an element, rho is nothing but 1 over the volume. So d rho by dt is simply dv by dt, or 1 over rho squared, minus 1 over rho squared times dv by dt. So the divergence of V is simply something like the change of the volume, and P times dV is the mechanical work done by the mass element, or the mechanical work which is put into your mass element. So this equation actually represents the first law of thermodynamics. So we end up with the first law of thermodynamics. Well, you may object here, because what have we done? It seems that we have proved first law of thermodynamics. You cannot prove first law of thermodynamics. So actually, our way of arguing with the energy balance was consistent with, so I would like to point this out. What we have done here is we have implicitly done an operation which is consistent with the first law of thermodynamics. We could have gone the opposite way, then we would have ended up with this prescription for writing down or for considering the energy balance. Here we took the opposite way. I tried to convince you about a plausible way to derive the energy balance by collecting all these effects, and it has been done in a way such that we came up with a law which is consistent with first law of thermodynamics. So we didn't prove actually first law of thermodynamics, which is not possible, but we have gone a way which is consistent with first law of thermodynamics, such that after this operation we in a consistent way arrive at the first law of thermodynamics. So that's just as a by remark. This is all consistent with first law of thermodynamics, and we end up with an equation which is suitable for being used in fluid mechanics, which we need for stellar pulsations, but which is, on the other hand, simply the first law of thermodynamics. Okay. So that's just as a remark here. So we end up with first law of thermodynamics, or some version of it at least, which is suitable for treating or for using it in a fluid mechanical environment or for stellar pulsations. Well, there are many forms of the first law of thermodynamics, and one variety of the first law of thermodynamics is to replace this term, the dq, the heat taken out or put into the system, which is, according to first law of thermodynamics, replaced by the change of internal energy and the mechanical work done to the system. Here I've written it in explicit form. The divergence of V can be written in a more familiar form through the continuity equation in the Lagrangian form, plus replacing the density by 1 over rho, and then you can immediately derive that this is du by dt, change of the internal energy plus p times dv by dt. So this is actually change of internal energy plus mechanical work, and this is, according to first law of thermodynamics, the heat energy which is transferred to the system. Now heat, the dq, might be, in a thermodynamic sense, be replaced by the change of the entropy. If we add, in some sense, the second law of thermodynamics, then the dq, the heat transferred to the system, is simply rewritten as T times the differential of the entropy. So this might be replaced by rho times T by ds by dt. So this is an alternative form, now relying on some further thermodynamic variables. So we replace this, the left-hand side, by rho times ds by dt, and s is the change of the entropy, and s is denoting the specific entropy. So in that sense, if we now replace this left-hand side by rho times t by ds by dt and go back to the upper form of the first law of thermodynamics, rho times ds by rho times t times ds by dt is then given by this term, which changes the heat content of our mass element, which is given by the energy generation and the divergence of the heat flux. Okay, so we have an alternative form of the energy equation. So some people use the upper form, some people use the bottom form, but this is quite nice and short. Rho times T times the time change of the entropy is given by energy generation and the divergence of the heat flux. Well, if the energy generation is not present, and if there is no divergence of the heat flux, then obviously the entropy is constant. That's what we call an adiabatic motion. If the entropy is constant, this is simply the condition, or this is simply another way of saying the motion proceeds adiabatically. It means that there is no heat exchange between the mass element and its surroundings. There is no heat gain or no heat loss in the system. And it means dq, or T times ds, is 0. It means the mass element does not exchange heat with its surroundings. an element not changing its heat content? What is a typical situation? What is needed if you have a flow and elements traveling through your environment? What is the situation when we can assume that this motion is adiabatic? What do you need for that? No heat exchange. The heat exchange must take much longer time than the element needs to travel along the flow. Then the adiabatic approximation is a good approximation. Then if the time needed for energy to diffuse, for instance, from inside to the outside, if this time is long compared to the time the element needs to travel along the flow, then we can assume it's adiabatic motion. Okay, then the adiabatic approximation would be valid. Okay. So if there is no energy transport, or the divergence of energy is of the heat flux is zero, and if epsilon is equal to zero, then entropy doesn't change, and we have an adiabatic motion. Okay, this is a special case of this equation. Now, what is left? Well, we haven't specified, let's go back, we haven't specified our external forces. There is still some unspecified force field or vector field which denotes the external forces, the external volume forces per mass. Well, we haven't specified that. We need to discuss a little bit about these external forces, in particular with respect to our astrophysical situation. Okay, so the forces which might be included in the external forces, well, we will neglect magnetic forces. We don't disregard magnetic and viscous forces, and we consider only forces which have a potential. That means forces which may be written as the gradient of some potential. So this vector field F, which may depend on the position and the time, it may be written as minus the gradient of some potential which depends on position and time. Well, there is one obvious force which we can write in this form and which we need, of course, in astrophysics. This is gravity, and gravity has a potential, and the gravitational potential is given by an integral. The gravitational potential, depending on r and t, is given as minus gravitational constants times the integral over the density at position x and t divided by the modulus of x minus r. This integral has to be taken over x, whereas the potential, it depends on r. So r appears only here. The rest of the variables in the integral depends on position x. Now we take the Laplacian operator acting on the gravitational potential. So the Laplacian operator acts on r. So we can take it underneath the integral because the integral is taken over x. So rho is not affected by the Laplacian, so what is left is rho of x, Laplacian acting on 1 over the modulus of x minus r. Okay, now I have to resort to some functional analysis. The Laplacian operator acting on 1 over x minus r is a delta function. It's minus 4 times the delta function of x minus r, and that means that this is simply this integral over rho, and the delta function will give rho at the position r and t. So I think everybody will be familiar with that analysis. So we end up with an alternative form for determining the gravitational potential, which is Laplacian acting on the potential phi is 4 pi times gravitational constant times the density as a function of position and time. The Poisson's equation for the gravitational potential. Okay, that's for the external forces which we need. There is another thing. Well, then we have to consider another point which occurs in stars and which is very important in stars. This is the energy transport. So it has to do with the heat flux and how the heat flux changes, or what determines the heat flux once we are in a star. Or you can have also this situation on Earth. You have different temperatures in different places of your environment. Then of course there will be a heat flux from high temperatures to low temperatures, and the same happens in a star. So we have to consider the transport of energy, or the heat flux which goes from higher temperatures to lower temperatures, how this heat flux depends on temperature gradients and so on. So energy transport is the next issue we have to consider, and we will consider energy transport in stars, at least in those environments which are important for pulsations in the so-called diffusion approximation. So we assume that the energy transport is described by a diffusion type equation. That means the flux is proportional to the gradient of some quantity. You can have diffusion of particles, then this would be the flux of particles, which depends, or which is proportional to the gradient of the density of the particles. If you have if the density of particles is not constant, then you will have a diffusion of particles going from high concentration to low concentration, and then we have a flux of particles depending on the gradient of the densities of the particles. And the same can be done with energy transport. Then we have the energy flux. The flux of heat will go from high temperatures to low temperatures. So the origin of the heat flux is a gradient in temperature. Whenever you have a gradient of temperature, we will have a heat flux. Of course, the heat flux goes from high temperature to low temperature, so there has to be a minus in front here. So heat flux is proportional to minus the gradient of the temperature, and anything else which we don't know, we condense into the diffusion coefficient. That's the problem is here, the diffusion coefficient. This is a problem to determine the diffusion coefficient, but we condense all our lack of knowledge into that diffusion coefficient. Okay, this is how we describe energy transport in the interior of a star, and this will be one of the main equations we have to consider once we consider stellar evolution. We will go to stellar evolution shortly, and we will also, this is also important once we consider energy transport in the framework of the treatment of pulsations. Okay, well, if we consider diffusion of photons, we can then make, you have to do a very extensive theory on how it needs some elaborate treatment of how the photons diffuse through your medium. Anything remains the same, but we can specify for the diffusion of photons, we can specify the diffusion coefficient in detail. For diffusion of photons, we have that this diffusion coefficient goes with the temperature to the third. Why does this temperature dependence, how does this temperature dependence come about? Yes, you can. Well, I said, for instance, for the diffusion of particles, the flow of particles, the flux of particles goes with the density of the particles. Well, the flux of energy should be proportional to the energy density. This would be the analog or the parallel argument. So the energy density is depends on temperature by the fourth power of the temperature. So the radiation, the energy density of radiation goes with temperature to the fourth, and so you can rewrite this energy density dependence in a temperature gradient, and if you differentiate t to the fourth with respect to the radius, then you get a factor of t to 3 times gradient of the temperature. So that's where the t to the third dependence comes from. Of course, you always have some constants. This is a radiation constant. This is speed of light, an additional factor here, and the essential quantity here, which determines the energy transport, is the so-called opacity. And to determine this opacity is a big business, because you have to take into account all the interaction between photons and matter. You have to consider various processes which go on in an atom, which absorbs photons, which re-emits photons, and all that is condensed in the so-called opacity. And it's a big problem, and it's a big business in astrophysics to determine this opacity. This opacity is the essential quantity in the energy transport equation. We'll come to the details of opacity later on. But this is the diffusion equation and the diffusion coefficient, which is used for the description of energy transport in a star. Okay, so this is another process. Well, diffusion is not the only way how energy is transported in the star. In a star, you may meet the situation. This is also meet in the Earth atmosphere. Sometimes you can see it once the weather is nice. You see that if the atmosphere is heated by the sun, then the blobs of air will rise because they become warm, and this is convection. And by this motion of blobs of material, you can transport energy, and this is called the energy transport by convection. Its origin is an instability of the stratification. So if you have stratification of density and temperature in Earth's atmosphere or in a star, then this stratification may not stay as it is, but it can become unstable, and then blobs of material will rise and some blobs of material will fall, and this motion then will transport simply by its macroscopic motion. It will take energy from the bottom and release it somewhere at the top, and then it falls down again and simply gets energy at the bottom and transport it again to the top. And this macroscopic motion, simply by the macroscopic motion of the matter, will contribute to the transport. And that happens also in a star. Once the stratification becomes unstable, convection sets in, and then we need to calculate how big is the energy, what is the energy transported by this motion. And this is the disappointing thing about it, is there is no theory about it. Well, people nowadays try to simulate convection. The problem is it would need a proper simulation of convection, would need an extremely dense grid. You have to go to very, very small scales, and this is still not possible. So direct numerical simulation of convection is not yet, perhaps it will never be possible to simulate numerically convective motion and convective transport. So what is left here is so-called mixing length theory. I would not like to address it as a theory. It's like an engineering prescription how to calculate the convective energy flux. So it is a summary, or it's several very reasonable physical assumptions which are taken together to provide a prescription how we might describe the energy flux, energy transport by convection. And actually this is one of the basic problems in stellar physics in general, and it's also a big problem for those people who deal with stellar pulsation theory. Convection is not, we don't know what to do with convection. It seems to work for hydrostatic stars. The mixing length theory seems to be quite adequate. It leads to reasonable results. There are many uncertainties left, but once it comes to a time-dependent convection, we are lost. So I have to disappoint you at this stage here. There is no theory of convection, and we don't know how to treat convection, in particular in an environment which is time dependent, like stellar pulsations. So the best thing is to go to stars which are not unstable with respect to convection and treat them. Then you are fine. But unfortunately, almost all stars have convection zones, and you are left with this problem. Okay, so just as a cautionary remark, convection is a big problem, and well, unfortunately, I cannot present you any decent theory here. Well, for completeness, I have to mention that we have in degenerate stars, there are some stars where we have heat conduction. It's not only diffusion of photons, but heat conduction, which is, so to say, the diffusion of those particles which have the biggest mean free path in degenerate stars. These are the electrons. So, and this process is called heat conduction in degenerate stars. But this is just for, we will not deal further with heat conduction in degenerate stars, just for completeness of the processes which contribute or might contribute to heat transfer. Okay, so this actually heat transfer or the energy transport is one of the basic of the main parts which also affect, which considerably affects the theory of pulsating stars. Okay, well, there's, for completeness, something is left. We can also change the chemical composition within a star. The chemical composition usually is changed by nuclear processes. There are no other processes which we can have in mind which change the chemical composition. And to calculate the change of chemical composition, we need to invoke nuclear physics. And in a very formal and crude way, I write it down here in the following form, in the Lagrangian sense. So d by dt of, in the Lagrangian sense, of the mass fraction of some species. This could be xi, I denotes the various species. This could be carbon, oxygen, hydrogen, helium. This is controlled by nuclear physics. The change with time of some species is given or depends on the concentration or on the mass fraction of any other elements. So xj denotes those nuclei from which the nucleus I is formed. So it depends on the mass fraction of other species necessary in the process, and on pressure and temperature. It depends also on the thermodynamics of the system. Xi is the mass fraction of element I. And the detailed form of this equation has to be provided by nuclear physics. It's a very complicated form, very complicated dependence on pressure and temperature usually. But I won't go into the details here. Okay, now we are almost done, but we still have not enough equations for the number of variables. So one equation is still missing, and this equation is provided by the equation of state, by the thermodynamics of the system. That means you have to specify an equation which relates the thermodynamic quantities. That means pressure as a function of density or temperature, or you take the inverse, you write it in the form that density is a function of pressure and temperature. This is the usual thermodynamic basis. So these quantities in the brackets are called the thermodynamic basis. Here the thermodynamic basis is density and temperature, and you express any other quantity in terms of density and temperature, and in this case the thermodynamic basis would be pressure and temperature, and then you write all the quantities in terms of pressure and temperature. For instance, here the entropy can then be expressed as a function of pressure and temperature. Well, this equation of state has to be provided by the thermodynamics. We have to consider what is how our stellar matter might be described, what is important, how these equations of state will look like in detail. We'll come to that later on, and I will give you some examples for the equation of state we use in the stellar environment. Of course, this is the equation which closes the system, and then we have enough equations and enough variables to solve the system mathematically. Of course, some functions still have to be specified, and we will do that later on. This is the opacity. You have to determine the opacity occurring in the energy transport equations. Opacity is also a function of pressure and temperature, and it is a sensitive function of chemical composition. So you need to know the chemical composition, and you need to know the pressure and temperature to determine the opacity. And the same is true for the energy generation rate, the nuclear energy generation rate. It also depends on pressure and temperature, and also on the chemical composition. So this needs to be calculated from atomic physics, and this needs to be provided by nuclear physics. Okay, well, then we are done. If we have all these quantities, well, our task now will be to apply all these equations to stellar structure in dynamics, and we have to solve the resulting mathematical problem. So we have now collected all the basic physics. That was our aim, our goal. We have done it. We have collected all that. There are still some open questions about opacity, equation of state, opacity, and energy generation rate. But in principle, now we could go and try to solve this system of equations. Well, there is obviously, these equations are too complicated. We cannot assume that we will have an analytical solution. We have to do it numerically, and there is again some disappointment, because these equations, even if you have a big computer, you can, so far it's not possible to solve these equations directly. So even in three dimensions, you cannot solve it. Oops. Nowadays. Okay, we are aiming first at a numerical solution, and I have to disappoint you. It's still not possible to do it in 3 dimensions. It's partially possible to do it in 1 dimension, so in spherical symmetry, and therefore we have to rely on some simplifications, on some approximations, and this is really necessary to solve the equation. But at the same time, even if we were able to solve all the equations in their complete generality, then the question arises, once we simulate the equation and we get the result, did we understand anything? If you look at the numerical solution, do we get some insight from the numerical solution? Well, we can just look at it and say, well, that's it. That's reality, of course, or it's close to reality or not. We can compare it to the observations, but we have not gained some deeper insight into the problem. A deeper insight into the problem can only gain if we simplify the problem, if we make analytical models for certain aspects, and then we can get some insight. Numerical solution may be fine for comparing with observations, but it does not tell you what's really going on. That's so this is not really a drawback, because we would not, that we cannot solve it numerically. It's not a drawback, because in order to gain some physical insights, we anyway would have to simplify the problem to solve partially the problems analytically. So it's actually not a drawback to consider simplifications and approximations. Okay, that's as a remark. Now let's again summarize the equations which we are going to solve. Well, we have mass conservation, the continuity now in the Eulerian form. We have the momentum conservation. This is Euler's equation here with the Eulerian form containing this non-linear term in the acceleration. This is remarkable in fluid mechanics. This non-linear term causes really much trouble in fluid mechanics, which this acceleration is balanced or is given by pressure gradient, and in astronomy or astrophysics and by the gravity. Then we have the energy conservation, or the first law of thermodynamics, either in the form using the internal energy, the change of the internal energy, and the work done, the work done at the mass element, or in the form using the entropy, the change of entropy, which is then governed by energy generation and the divergence of the heat flux. This is the energy equation. Adiabatic motions are characterized by constant entropy. Then we have the energy transport, for instance, by radiation diffusion. Then we can specify the diffusion coefficient. And we have the gravity controlled by Poisson's equation. And nuclear processes, the change of mass fractions is given by nuclear reactions. And we have to specify an equation of state. Here I have included also the dependence on chemical composition, not only the dependence on pressure and temperature. And of course we need to specify the opacity and the energy generation rate. That's just to summarize what we have to solve and how to proceed now with approximations, with simplifications, to gain some insight into the problem. Okay? Well, first simplification we do not consider a three-dimensional configuration, but we reduce the geometry from a three-dimensional configuration. We reduce the geometry to a spherical symmetric configuration. This is not too bad. If we look at our sun, it seems to be a quite nice sphere. So that might motivate that this simplification is not too bad. We simplify first the geometry, trying to keep all the physics. The physics, try to keep as much of the physics as we can, but simplify the geometry. So going to spherical geometry. Okay, well then let's stop here and go to the simplification of geometry in the next lecture.
Yeah, so now let's start the lecture number 2 of this day 2. Okay, Professor Glatzel, over to you.
Thanks. First of all, I would repeat my encouragement to you to ask questions and to object and tell me if something is wrong. So if I'm going too fast, please tell me. If I'm going too slowly, please tell me. If I'm doing anything wrong, please tell me. If you have objections, I'm happy to receive them. And please, if there's something unclear or you have questions, please immediately ask. I have not received, yesterday I have received some questions, but today, this morning, there was no question at all. I hope this is not due to the fact that it was not clear enough. So if it's not clear enough, please tell me and please interrupt if you have questions. Okay, we saw in the last lecture that the most general form of the equations would be either difficult to solve numerically, and in addition we would not receive too much understanding, too much insight if we just solve the equations numerically. So the strategy would be we simplify the problem, first of all to get into a position to solve them really numerically, and secondly to gain with a restricted system, with an approximated system, more insight into the physics. The first approximation we do is keeping as much of the physics as we can and simplify simply the geometry. Simplifying geometry is reducing the problem to a one-dimensional system, a one-dimensional spherical system, by adopting spherical symmetry for our star and also for the motion and the dynamics of the star, and introduce spherical polar coordinates r, theta and phi, and all quantities will only depend on the radius r. In one-dimensional systems it's convenient to adopt the Lagrangian description. This is not true for three-dimensional systems. That often the Eulerian description is more appropriate, but in one-dimensional systems usually the Lagrangian description is more favored. Okay, so we adopt the Lagrangian description, and first of all we introduce a new Lagrangian independent variable. So far we have taken the initial position vector of a mass element as the Lagrangian coordinate, rather than taking r0, which by r0 we describe the initial radius of our mass element as the Lagrangian variable. We consider the mass contained in a sphere of radius r as a variable. How is it done? Well, the mass inside a sphere of radius r, this would now be either r is now the Lagrangian dependent variable as a function of r0 and t, integrated. Mr is the integral of density over the volume element. The volume element in spherical coordinates would be 4 pi r squared dr. So we have to get the mass inside a sphere of radius r, we would have to integrate rho times 4 pi r squared dr from 0 to the actual position of our mass element r. Well, this is, of course, since we have mass conservation, this should be the same mass which is contained in the sphere of radius r0, because there is no way to lose mass once the radius of our mass element change. So this should be exactly the same mass which is obtained by integrating rho times 4 pi r squared dr in the initial position. So what we change is simply the radius from r0 to r. This is the actual radius and this is the initial radius, and the mass contained at time equals 0, contained in a sphere of radius r0, will be the same mass. It's denoted here with mr naught that should be equal. Because there can no mass can get lost or gained, this mr should be equal to mr naught should be equal to mr due to or as a consequence of mass conservation. So mass conservation is simply that this dmr by dt should be 0 or mr is equal to mr naught. So instead of taking r naught as the Lagrangian variable, we could also equivalently use mr, which is mr naught, mr equals to mr naught as a new Lagrangian variable. So this is time independent and it ensures mass conservation, and at the same time it replaces r naught as a Lagrangian variable. So it's replacing r naught with mr naught, and mr naught is equal to mr due to mass conservation. So this might be a new variable, a new Lagrangian variable. M is independent, and r, now the radius, where we can replace or we can write the radius instead as a function of r naught, like here, we can write the radius as a function of the Lagrangian variable mr and t as a dependent variable. Radius is now a dependent variable, the independent variable is mr, and it's a Lagrangian way of describing the system. Okay, there is actually a differential relation between the dependent variable r, the Lagrangian dependent variable, and the Lagrangian independent variable mr, simply by differentiating this integral with respect to the radius. So we get dmr by dr is simply the integrand, which is rho times 4 pi r squared. Okay, so we have a differential relation between depending variable r and independent variable mr in the Lagrangian picture, which is given by 4 pi r squared rho. This is simply the definition of mr. Or if we invert this relation, we can make a rewrite it in terms of dr by dmr. It's simply taking the 1 over dmr by dr, which leads to dr by dmr is now 1 over 4 pi r squared rho. And this relation might now be used to change between the variables r and mr to transform from the variable radius to the variable mass. So to say we are now going to change, or we can transform from the position as Eulerian position as an independent variable to the Lagrangian variable mr. So, and the transformation is given by dr by dmr. So d by dmr is 1 over 4 pi rho squared times d over dr. This might be used as a transformation from radius to mass. Yes?
What sort of advantage it gives when we go from this using independent variable r naught to the independent variable as mass?
You will see in a moment what will happen, how the equations can be simplified, and what the advantage is how we get a more convenient description. Okay. May I just ask for a few seconds? You will see it in a moment. Okay. First of all, of course, we are interested in gravity. Gravity, in an Eulerian sense, is given by the derivative of the potential with respect to r. R is now the Eulerian variable, and we have the equation which determines the potential, which is Poisson's equation. We drop the theta and phi terms because we assume spherical symmetry. So the radial part of Laplacian operators is d 2 phi by the r squared plus 2 over r d phi by the r. All these derivatives with respect to theta and phi are 0 because we assume spherical symmetry. And according to Poisson's equation, this is 4 pi g times the density. Well, we rewrite it a little bit. This expression might be written as 1 over r squared d by the r of r squared d phi by the r. You can convince you immediately that these two expressions are the same. Okay, now we multiply the equation with r squared and integrate it. So we have, on the right hand side, we have 4 pi g rho times r squared integrated over dr. Then this should be r squared times d phi by dr. The right hand side is g times mr, just by definition of mr. Or we get the phi by dr, which is the gravity. In the equation of motion, only the gradient of the potential appears, so the gravitational force or the gravitational acceleration. The phi by dr is gmr over r squared. So we have the gravity, and this is the only point where the gravity appears in the equation of motion, is given in a closed algebraic form as gmr over r squared. Mr is the independent Lagrangian variable, and r is the dependent Lagrangian variable. Whereas in the Eulerian picture, we would have to integrate this in a much more complicated way. So mr is, in the Eulerian sense, it's an integral, and it's difficult to deal with. Here in the Lagrangian sense, it's one of the variables. The Lagrangian way is just avoiding this integral and avoiding an additional integration. This is the advantage, one of the advantages to go to the Lagrangian picture and choose the mass as an independent Lagrangian variable. It's okay. Does it answer your question now? That's one of the advantages. We omit one integration or one differentiation. We reduce, so to say, the order of the differential system by having done already one of the integrations and using these integrated variables as one of the new variables. This is the trick. Okay? Does it? Okay. So the next assumption we go from the heat flux, which has only one component in the radial system. F theta and F phi are 0. There's only one component, which is the radial component of the flux, and replace it by the quantity which astronomers are used to, which is the luminosity. So in a spherically symmetric system, we can just get the luminosity, the energy per time which leaves the star or which goes through the star, by multiplying with the surface of a sphere times the flux per area and time which goes through the star. So we usually replace the flux by the luminosity. It can be done for a spherically symmetric system. Okay. Then we use pressure and temperature as the thermodynamic basis. That means we write the entropy as a function of pressure and temperature. And now I have to resort to some thermodynamic relations. Well, TdS is written now in the form that it's Cp, it's the specific heat at constant pressure, times the differential of the temperature, minus delta over rho times the differential of the pressure. Delta is defined, now I have to introduce several thermodynamic quantities. Delta is the logarithmic derivative of density with respect to temperature at constant pressure, with a minus. And alpha, for completeness, is the logarithmic derivative of density with respect to pressure at constant temperature. You are probably not used to this notation. Why do we use logarithmic derivatives? What is a logarithmic derivative? Well, a logarithmic derivative is, or are you familiar with that? Okay. So logarithmic derivative means, well, if we have something like d rho over rho, this is d log rho, because d log rho is simply the derivative of log is 1 over. So this is 1 over rho times d rho. So all these quantities, d rho by d rho, can be written as d log rho. And logarithmic derivative means, for instance, let's take the logarithmic derivative here, alpha d log rho over d log rho over d log P at constant temperature is simply d rho by dP at constant temperature. This is familiar. This is the derivative of rho with respect to pressure at constant temperature. And to get a logarithmic one, it's P over rho. So this is dP over P is d log P, and d rho over rho is d log rho. Why do we use these quantities? First of all, they are dimensionless, because dimensions of rho, dimensions of P cancel, and they are dimensionless quantity, and usually logarithm is a small function, so they are of order unity. So we get, using this notation, these alphas and deltas are dimensionless quantities, and they are of order unity. So that's convenient, for instance, also for numerical computations. Okay, how do these quantities come? Where do they enter? They do enter if we write, for instance, rho as a function of pressure and temperature. So let us write now rho as a function of pressure and temperature. So we write rho is function of pressure and temperature, and we take the differential of it. Usually in thermodynamics you always work with differentials. So d rho is d rho by dP at constant temperature times dP plus d rho by dt at constant pressure dt. This is simply taking the differential of an unspecified relation of the type rho as a function of P and T. Now, how do these coefficients come about? We divide this equation by rho, and then d rho by d rho. So this will be 1 over rho here, 1 over rho, and we we rewrite in terms of dP over P. Then we have to write P here, and here we have a dt over t. Okay, we go to the relative changes, and what you have here then is d log rho by d log P at constant temperature. So this is d log rho by d log P at constant temperature, and this here is d log rho by d log T at constant pressure. And these coefficients are the alphas and deltas. So this is defined as alpha, and this is defined for convenience with a minus delta. This is the definition of these coefficients. We will come across many of these definitions. So for instance, if we write the opacity as a function of pressure and densities, we can do the same as for the density. Then we get d log kappa as a d log kappa by d log P, which is a kappa sub P, or d log kappa by d log T. This is kappa sub T. These are derivatives which are dimensionless and which are of order unity. So this is usually done for any quantity what I have done here for the density might be done for the kappa as a function of p and t, or it might be done for the epsilon as a function of p and t. We define all these logarithmic derivatives in the same way. Okay? So if you are not yet familiar with that, this is how the thermodynamics is typically addressed in stellar physics. Okay, now I promised I would explain what is how this t times ds by dt is one of the terms which appears in the energy equation. How we replace this by Cp by times the time change of temperature and the time change of pressure. So we can, by this relation, replace the time derivative ds by dt, which appears in the energy equation, by the time derivative of the temperature and the time derivative of the pressure, which includes thermodynamic quantities like specific heat at constant pressure and this strange coefficient delta here. So we have to somehow prove this relation. So let's go back. Okay. What I already wrote down is here d rho might now be written as d rho by dp at constant temperature, dp plus d rho by dt at constant pressure times dt. And as done before, we go to the relative changes, which is d rho over rho, which is alpha times dp over p plus or no, minus delta times dt over t. Now we consider the entropy as a function of pressure and temperature. So we have in this way dq, the change of the heat content of our mass element, is given by T times ds. This is thermodynamics. The change of heat content is given by T times ds, and now we write ds in the same way as we did for the density. So we say ds is ds by dt at constant pressure dt, and plus t, of course, t times ds by dp at constant temperature dp. Okay, if we now consider heat transfer to our mass element at constant pressure, that constant pressure means dp is 0. So we have dq is equal to t times ds dt ds by dt at constant pressure dt. dp 0 means this term is 0, constant pressure. That means dq is something like dt. Well, if we change the heat, if we put heat into our system and the temperature changes and the pressure is 0, then the coefficient of the change of the temperature will be the specific heat at constant pressure. So what we have seen then, that the specific heat at constant pressure is simply one of the derivatives of the entropy with respect to temperature. So we have now seen by this experiment that Cp is T times ds by dt, and this is the first part I wanted to prove here. So T times ds is simply Cp times dt. There's the second term is left, which was minus delta over rho. So how do we prove that T times ds over dp is something like delta over rho? Well, it requires a little bit more effort. Okay. Well, let's go to the first law of thermodynamics. dq is the change of the internal energy minus p over rho squared times d rho. This is the pdv term, and this is the change of the internal energy. Now let's express du and d rho in the same way by dp and dt. So let us assume that the internal energy depends on pressure and temperature and also the density. We have done that already above. So this has been done for the density already. It's already done. Express it in terms of dp and dt and do the same for the internal energy. Okay, what are we left with? So this is du by dt at constant pressure times dt plus du by dp at constant temperature times dp. Now the same for the d rho. This is minus p over rho squared d rho by dt at constant pressure minus p over rho squared d rho by dp at constant temperature. Okay? Well, and now we compare our formulation in terms of the entropy derivatives with these derivatives. Okay, so let's go to the, I hope I will, oops. Okay. So dq is either in terms of the entropy given by these two terms, or it's given by these two terms. Now we take the coefficient of dt, and therefore t times ds by dt has to be equal to that bracket, and t times ds by dp has to be equal to that bracket. You agree? Okay, let's write it down. And what we are aiming at is determining this derivative. Okay. So we have two identifications. T times ds by dt is du by dt minus p over rho squared d rho by dt. And the second one is T times ds by dp is equal to du by dp at constant temperature minus p over rho squared d rho by dp at constant temperature. Two equations. And what we are doing now, we differentiate the first equation by pressure at constant temperature, and we differentiate the second one by the temperature at constant pressure and subtract these two from each other. So differentiate the first by dp minus differentiate the second one by dt. Okay? What happens? For instance, take this term du by dt and times or differentiate it again by dp minus du by dp differentiate by dt. What is that? If you take the difference, it's 0. So these two terms cancel. Similarly, if we take if we ignore this temperature, if we differentiate this with respect to t and p minus differentiation with respect to p and t, these terms should cancel. So the first, let's consider first the left-hand side. We differentiate this this quantity with respect to temperature at constant pressure. Then we have we have to differentiate this with respect to pressure at constant temperature. If we differentiate temperature with respect to pressure at constant temperature, it's 0. Okay, this is 0, and the second one will cancel with that. And so this has to be differentiated with respect to pressure at constant. This has to be differentiated with respect to temperature at constant pressure. If you differentiate temperature with respect to temperature, it's 1. So we have what is left on the left-hand side in this differentiation and subtraction is minus ds by dp at constant temperature. And that's the quantity we want to determine. Okay? So what we have on the left-hand side, what is left is minus ds by dp at constant temperature. Anything else cancels. We already saw that these cancels, and if we differentiate these by temperature and pressure and subtract the same term with the differentiated with respect to pressure and temperature, so they will also cancel. So what is left is the differentiation of this p over rho squared, which is left. So we have, in this case, we have this term, it's minus d rho over dt by p, and here we have left this d rho over dp at constant pressure. We have to differentiate this quantity with respect to pressure. This gives first dp by dp is 1 over rho squared, which is left. And then we have to differentiate the 1 over rho squared, which gives minus 2 over rho cubed times d rho by dp at constant temperature. That's left here. The same is done here, and it has to be differentiated at constant pressure, so this term will not appear. This will be 0, and it's only the differentiation of 1 over rho squared which is left, and we have then the minus p 2 over rho cubed times d rho by dt at constant pressure. Okay, so what we are getting is, well, these two terms, d rho by dt times d rho by dp we have here, and here we have d rho by dp times d rho by dt. This is identical. So these two terms cancel, and we are left only with minus d rho by dt at constant pressure times 1 over rho squared. So everything else is gone. Okay. What is left now? So minus ds by dp at constant temperature is given by minus d rho by dt times 1 over rho squared. Or if we rearrange it a little bit, then taking out the minus signs, t times ds by dp at constant temperature is given by t over rho times d rho over dt at constant pressure times 1 over rho. And this is simply, this term here is d log rho by d log t at constant pressure times 1 over rho. And according to the definition, this is minus delta over rho. So we have proven that this t times ds by dp at constant temperature is minus delta in extension, because such calculations appear in stellar physics at any time. You have to transform back and forth, and you have to be aware of such calculations. So you have to get used to this formalism. Sorry about it. It was a little bit of algebra, but it was a little bit of helpful thermodynamics. Okay, so what we have proven now is that, first of all, this term is proportional to Cp. This is the specific heat at constant pressure, and this is something like minus delta over rho. Okay, so let's go back. Let's go back. TdS now we have proven can be written as Cp times dt minus delta over rho times dp. So we replace in the energy equation, we replace the derivative with time of the entropy by the derivative of time of temperature and pressure. This is one step which is done just to meet the usual notation. We could have stayed with the entropy as a variable, but usually people use temperature and pressure as the variables, and therefore the usual way or the conventional way to describe this energy equation is done in terms of temperature and pressure. This is just a tribute to the general convention. There's not much physics behind it, except for transforming between the different thermodynamic bases. Okay, the next transformation which is done is taking the dr by dm, so to say the equivalent of the mass conservation, take this definition of the mass mr for a transformation from the Eulerian variable r to the Lagrangian variable mr. And of course, in this context here, dt, whenever we have d by dt, even if we write it as a del over del t, it's meant in the Lagrangian sense. We are fully in the Lagrangian scheme. So sorry about this. I would like to avoid confusion, but usually it's in stellar physics they use del by del t, even if it's a Lagrangian time derivative. Okay. So in this context, the del by del t refers to the Lagrangian time derivative. So what do we get in the end? We get the equations for spherically symmetric structure and dynamics of the star. We already saw the first one, which is simply the definition of the mass inside sphere of radius r. So you may regard here now r as the dependent variable, and mr is the Lagrangian independent variable, which is given by 1 over 4 pi r squared rho. You may regard this as an expression for mass conservation. You could also say it's simply the definition of our mass coordinate or coordinate mr. What we are now doing, we replace the pressure gradient, which is appearing in the Euler's equation. We replace it dp by dr by dp by dmr using this as a transformation equation. So d by d, you just have to multiply d by dr by this expression, and then you automatically have the dp by dmr. You get this factor 1 over 4 pi r squared for the gravity. The gravity is now written as minus gm over r squared. If you multiply it with 1 over 4 pi rho squared, you get a 1 over 4 pi r to the fourth. The density is gone because there is a 1 over rho here, 1 over rho times the density, and the term left is the acceleration now not in the Eulerian description, but in the Lagrangian description. In the Lagrangian description, it looks much simpler than in the Eulerian one. We don't have the v times nabla v term. In Lagrangian term, we just have the acceleration. Okay. I think it's a simple way. I don't need to do this in detail. You have to transform from d by dr, the pressure gradient, using this transformation, and there is nothing else behind it. Okay? That's for the equation of motion, which becomes pretty simple here. Then we have, instead of the gradient of the temperature, instead of the divergence of the flux, we have the derivative. We replace the flux by the luminosity, and then the divergence of the flux may be written as the gradient of the luminosity. The gradient of the luminosity is again replaced by the gradient of the luminosity in terms of the mass coordinate. So we get dl by dmr instead of divergence of the flux, which is equal to the energy generation rate minus the t times ds by dt, and the t times ds by dt is now replaced by specific heat at constant pressure times the time derivative of the temperature plus delta over rho times dp by dt. Okay, so this is the derivative of the entropy, and it's the dq. This is the divergence of the flux, and this is the energy generation rate. So that's where these terms come from. Okay, and finally we have the diffusion equation for energy transport. We replace the gradient of temperature with a gradient with respect to the mass coordinate, with the Lagrangian mass coordinate. This gives these 4 pi r squared dependencies. So there are these 4 pi's are hidden, r squared are hidden here. And we replace the flux by the luminosity. This gives another 4 pi r squared, and we are left then with the expression on the right hand side, which tells us dt by dmr with respect to the Lagrangian variable is proportional to minus the luminosity, And the essential quantity which is entering here is the opacity here on the right-hand side. Of course, we have ignored convection here. This is just for radiation diffusion. To complete the system, well, there are if we include nuclear processes, then we have to take into account the change of mass fraction. Here the time derivative is a Lagrangian one, which is a function of the mass fractions of all nuclear species which take part in the process, and the pressure and the temperature. So this equation is essentially not changed if we want to take it into account. Okay, like before, equation of state, the nuclear energy generation and the opacities have to be taken from atomic and nuclear physics. Okay, that's the complete system. I hope I didn't forget. Okay, this is the equation which we have to solve, both for the stationary structure of a star and for the dynamics of a star. Now, if you look at these equations, there are time derivatives appearing here and on 3 places. One of them is the mechanical acceleration, which contains this time derivative here. Well, this is mechanics, so it should be associated, of course, with one of the typical stellar timescales. And the mechanical timescale, or the shortest timescale which we know of, is associated here with the loss of mechanical equilibrium. So this derivative is associated with the dynamical timescale of the star. There are 2 time derivatives appearing here, or maybe written as a single time derivative of the entropy here. This has to do with the change of the heat content of the stellar matter. So this is related to the thermal timescale or the Kelvin-Helmholtz timescale. This is the green ones, and there is a third appearance of time derivative here. This has to do with nuclear processes, so the timescale which enters here is the nuclear timescale. So you recover the time, once you're looking at the system of equations, you recover the 3 timescales which are important for stellar structure and evolution. Okay, once we are interested in pulsations, then of course we have to consider, or we must not ignore this term. This is important once we are looking for stellar pulsations. On the other hand, if we are looking for a star in hydrostatic equilibrium, then we simply drop this term. Stellar equilibrium means the gravity is balanced by a pressure gradient. And this is called hydrostatic equilibrium. If we consider a star in equilibrium, then we usually drop this term. This is done in stellar evolution. Stellar evolution assumes that the star is in hydrostatic equilibrium. So we drop this term and only consider the green time derivatives and, of course, in particular, the blue ones. So stellar evolution, for stellar evolution, thermal timescale plays a role and the nuclear timescale plays a role, and the dynamical timescale is we get rid of the thermal timescale by simply ignoring the acceleration here. On the opposite, if we are interested in stellar pulsations, what we do? Well, stellar pulsations occur on a timescale which is much shorter than the thermal timescale and the nuclear timescale. So we may ignore, be careful, it's not completely true, but we may surely assume that nuclear processes don't take place or are not important during one pulsation period. It just takes too long for them to operate, so we can ignore nuclear processes once we are considering stellar pulsations. We assume that the mass fractions of our species are constant. And in some cases, we even can assume that epsilon is 0. We do not consider the energy generation, because nuclear processes are too long on timescales which we are interested in, which are very short, which are at most a few hundred days, in a few hundred days compared to a nuclear timescale of 10 to 10 years. We can assume everything is constant. The same is true partly. We will come to that. We can partially assume that these terms are 0 once we consider pulsations. When can we really assume that this term is 0? It is the time derivative of the entropy. So once we ask for the situation when this term can be regarded as 0, what would be, once we assume that the changes during pulsations might be adiabatic. One has to check this, whether it's really true that we can assume that this term vanishes, that we have adiabatic motions. We'll come to that. It's not always true. For pulsations, partially we have to take into account this term, but there are stars where this term might be ignored. For instance, for the Sun, it's quite perfect to ignore this term. You get perfect results. There are other stars which also are close to adiabatic changes of state, but there are stars where this is no longer true. We'll come to that later on. So once we do stellar evolution, we ignore the red term. The red term, in any way, we consider only these long time scales, thermal time scale, nuclear time scale. For pulsations, we have to take into account the dynamical term, and partially we take into account the change of heat content, the thermal time scale. We can ignore the nuclear time scale. Okay. So contained in this system of equations are also the equations of stellar evolution. It covers both, of course, radial symmetry is assumed from the beginning. It assumes stellar evolution that is usually done in a spherically symmetric way. So these are the equations of stellar evolution, and these are at the same time the equations which we have to solve once we consider radial pulsations. The difference is just ignoring one or the other term, one or the other time derivative. Okay. Yeah, that's it. Okay, we have done this already. So, well, I was told you might not be that familiar with stellar evolution. So what we are doing now is, having arrived at these equations, which may also be used for stellar evolution, we make a short digression on stellar evolution, and we will consider some of the basic effects in stellar evolution. This is, on one hand, necessary for understanding how a stationary stellar model looks like, and we use static or hydrostatic equilibria as an initial point for studying stellar pulsations. So stellar pulsation studies always start with a stellar model. This stellar model might be taken from stellar evolution, or might be has to be taken from a consideration of these equations with the accelerations having been put to 0, and that's the starting point. And so in that sense, it's useful to get some information about stellar evolution, and therefore we make a short digression on stellar evolution. questions? Yes.
While introducing different processes like diffusion. Yeah, so while introducing different processes like diffusion and convection, I observed that you took the assumption of opacity.
Yeah.
Why is it required?
Okay, it's not an assumption. It's a well, we describe in the process of energy transport in terms of a diffusion process. And so we have flux is proportional to minus the gradient of the temperature.
No, sorry. Let me rephrase. My question is different. Opacity was introduced later.
Yes.
I remember now. Optically thick.
Yes.
That. Optically thick. Why?
Well, you could also consider the optically thin part of the star, but what is usually, well, there are two types of astronomers. The ones which deal with the atmosphere of the star, and ones which deal with the interior of the star.
Okay.
And the domain where these two guys operate is cut or is confined by the photosphere. Anything that lies below the photosphere is the subject of stellar interiors, and anything above is to those guys with stellar atmospheres. And once we do stellar evolution, this is usually done is everything below the photosphere. So the photosphere is for those people dealing with stellar interiors, and also for those who do pulsations, is the outer boundary of this domain is the photosphere. Well, it would be nice if we could extend also to the optically thin regime, but then the equations of radiation transport become very, very complicated. And just to refrain from having to deal with the complete radiation transport, people usually restrict themselves to regions below the photosphere where the radiation transport can be done by a diffusion approximation.
Thank you.
Actually, this is a problem because the photosphere, for those doing the interior of the star, the photosphere is not, it's just the outer boundary of the model, but it's not the outer boundary of the star. And so what do we need to assume as a boundary condition at the photosphere for the interior? It's ambiguous because it's not the physical boundary, and there are several good arguments which should be the boundary conditions there, but in principle they are ambiguous, and you cannot say, well, you have no strict mathematical way to prove which is the correct outer boundary condition. It's a problem. It occurs with the boundary conditions because, well, it's exactly what you addressed in your question. You should, in principle, you should take into account both the interior of the star and the atmosphere. But
One
that's
more
usually
follow-up question. So when this pulsation is happening, so since you said that optically thick is within the photosphere, right?
Yes.
So is there possibility of lag between the contraction of the star and the photosphere also?
Yeah, we even have the problem in a pulsating star. In a static star, it's quite okay to put the photosphere where Stefan Boltzmann's law is valid. Okay, but if the star starts to move, then also the photosphere will move, and it will move. It will not only be at the previous outer boundary in the Lagrangian sense, but it could move within, or could move to another Lagrangian position. And we do not exactly know where and how to define the photosphere then. So this is a problem once we once we come to a time-dependent pulsating star. Does it? Okay, it's a problem. I agree. Okay. Okay, now let us start with stellar evolution, with a small digression on stellar evolution. So I have to... Okay, well, stellar evolution, as we already learned, is governed by the equation of spherical symmetric structure and dynamics, with the additional assumption that we have hydrostatic equilibrium. That means the acceleration term is zero. The pressure gradient is balanced by gravity. This is the mechanical equilibrium. Well, the relevant time scales are thermal and nuclear, that's we already seen, and stellar evolution typically occurs on long time scales which are not accessible to human beings. 10 to 7 years, 10 to 10 years, it's not accessible. So what we cannot follow the stellar evolution, which we calculate by numerical integration, for instance. It proceeds on timescales of 10 to 7 to 10 to 10 years. So how do we compare it with observations? Well, we have to, concerning a comparison with observation, we have to keep in mind what we see on the sky is never the evolution of the star. We see different stars at a different stage of evolution. So we see what we see in a star is a snapshot of the evolution at today's time, plus minus 10, 20 years. So we see snapshots, and we have to connect all these stellar stars which we see in the right way, so to give you the trace of, or put them on an evolutionary track of which you calculate and put them at the right position. So it's the comparison of the theory of stellar evolution is done by taking a huge big amount of observation, huge big amount of stars, and keeping in mind these are stars at the different stages of evolution. They may have had different initial masses, and now we put them together and try to get a picture which relates to the stellar evolution, where we follow a single star along its evolution on timescales of 10 to 7 or 10 to 10 years. So it's it might be in sometimes rather complicated where to put a star, what is the evolutionary stage of a star. It's sometimes pretty difficult, but this is the only way we can proceed, because we do not have access to these very, very long time scales. Okay, so this is the basis of what we are considering here. Well, I have listed here some literature about, there are many more books here. I have taken pictures, Cox and Julie. You can never read this book because it's that thick. It's just for consulting. If you want to know some physics about a particular problem, go to this book. You will find everything. Okay. This is very thin, but you can't read it as a textbook. It's impossible. Okay. So what we'll do now for the next few lectures is we will briefly comment on stellar parameters. Then we need to discuss, this is also necessary for later use, we will discuss the equation of state in more detail. We will have to discuss the opacity. This is left. It's very important for stellar pulsations. We will comment a little bit on nuclear burning and the energy transport, because that touches also some problem which appears again in stellar pulsation theory. The stability of stratification, energy transport, stability of stratification comes in again if we consider G modes later on. So we have to deal a little bit with that, and then we'll briefly show how the evolutionary tracks proceed in the Hertzsprung-Russell diagram. And then I would like to comment on some very basic elements of stellar evolution. which is the virial theorem, which will also be addressed in the one of the tutorials, the mass luminosity generation, luminosity relation, and then the effect of degeneracy. These basic elements are maybe connected with the basic questions we may have once we consider stars. For instance, well, if we look out out of the window, we see the sun is shining. So one naive question would be, why do we see the sun shining? What is the reason, the physical reason that the sun shines, that the sun gets energy or puts energy to us on the earth? So what would be your answer to this question? What could be the answer to that question? Or more general, why does a star radiate? All stars radiate, the sun radiates, we live from that. Why does a star radiate? What is the reason? How would you answer that question? Some suggestion. It doesn't need to be wrong. It doesn't need to be right. A source of energy. Okay, there is a source of energy. That's the reason. Let's keep that in mind. Another. Pardon? I haven't understood. Nuclear fusion. Yeah. Okay. Nuclear fusion. That's. I think this should be on the same direction. Nuclear fusion, energy production within a star. Okay, let's keep that in mind. This is one of the basic questions of which you would ask. Actually, I expected this answer, and I can, in anticipation, I say it's not correct. There's another reason for a star to radiate. But keep this in mind. It's a very intuitive answer, and it seems to be plausible. Everybody would say this, but if you know a little bit more about astrophysics and stellar physics, the answer is a little bit different. So keep it in mind. So we will come to that, and we will see why a star radiates. This is one of the questions which we try to solve. And another question would be, why does a star evolve, and how does it evolve? The main question, or the essential question, is, why does a star evolve? Why cannot it stay forever as it is? Why does the star have to evolve? These are the questions which I like to somehow address as some basic elements. And this will continue, or this will contain then some physical arguments how we can answer and how we have to answer these questions. We have to stop? We have to stop, or is there some time left?
No, we don't have time now.
Okay. Okay, so let's continue here this afternoon. Everybody, and welcome back to Stellar Pulsations. We started this morning with a digression on stellar evolution, and I promised you to cover some selected problems of stellar evolution, which are, so to say, or in a certain sense, also connected to stellar pulsations. Stellar evolution and the construction of stellar models is a prerequisite of the study of stellar pulsations. So we should know a little bit how stellar evolution proceeds, what are the main outcomes of stellar evolution, and how do we construct stellar models. Okay, there are several topics. The first one is we should consider the stellar parameters and their limits, possibly, and the physics which constrains the stellar parameters. Okay, so let's turn to the apparent stellar parameters. Well, the star has a chemical composition. This means we have the mass fractions of different nuclei are prescribed or are observed, and we can take the chemical composition observed to construct the stellar model. In particular, our equation of state and the nuclear energy generation rates and the opacities, they will depend sensitively on the chemical composition. So we have to know how many hydrogen, how many helium, and how many of the heavy elements are within the mixture which make up our star. Well, the next obvious parameter of a star is its mass. The sun has a mass, any other star also has a mass, which is usually of the order of the mass of the sun. Some stars are much less massive, and some stars are more massive than our sun. Then what we observe is the brightness of the star, and for a theoretician, it's not the brightness of the star which we would like to use as a parameter, but we would like to use the counterpart of the absolute magnitude of the star, which in a theoretical sense is its luminosity, the energy per time our star emits over the entire spectrum. So this is the complete energy output of the star in terms of energy per second in all integrated, so to say, over all wavelength range. Another parameter is the effective temperature. For an observer, it's the color or the spectral type of the star. So we know there are blue stars and red stars, and the difference between them is their effective temperature. In defining the effective temperature, we've already made use of a relation between the parameters of the star. There is another one, of course, which is the radius of the star, and there is a relation between the luminosity and the radius and the effective temperature, which is given by the fact that a zeroth approximation to any star and its radiation is that a star radiates as a black body. If a star is considered to first or zeroth approximation as a black body, then the flux means the energy per area and second emitted from the star will be proportional to the fourth power of the temperature, and the position where this flux is emitted in the star according to the black body law is the effective temperature. So the effective temperature is defined by assuming that the star radiates as a black body, and the position in the star where the temperature is equal to this black body temperature is called the photosphere. So the photosphere, the star has a temperature which is equal to effective temperature, and the effective temperature is gained by the approximation that the entire star radiates as a black body. If we transfer it from the flux to the luminosity, then the luminosity is the area of the star or the area of the photosphere times the flux. This means that the luminosity then should be proportional to the sphere, to the surface of the photosphere, which is its radius squared, proportional to its radius squared. And therefore, the luminosity has to be proportional to radius squared times the effective temperature to the power 4. A convenient representation of, say, luminosity and effective temperature, maybe you who has done some astronomy will know it, is the Hertzsprung-Russell diagram, where the observer plot the magnitude, sometimes the apparent magnitude, it's better to put the absolute magnitude against the spectral type or the effective temperature. For historical reasons, the hot stars are on the left-hand side of the diagram and the cool stars are on the right-hand side. So we can introduce in this diagram lines of constant radius. Maybe this is known to many of you, most of you. Well, luminosity, theoretician would take the luminosity and the would take the effective temperature, where the effective temperature goes that way. The high effective temperatures are on the left-hand side. And actually, it's a log diagram, so log L against log T effective, and we have the Stefan Boltzmann's law valid in this diagram. So this is the usual way representing at least these two parameters together with radius in the Hertzsprung-Russell diagram. The mass, of course, is not so easy to display, and it's one of the parameters which are very difficult to determine. Usually the mass is known not to the same degree as luminosity and effective temperature. In this diagram you can plot the lines of constant radius. So we have luminosity is proportional to r squared times the effective temperature to the fourth. So in a log-log diagram, lines of constant radius would be lines where log L goes to, log L is 4 times log T effective. Because we take it the opposite way, it's lines of slope minus 4. So these are curves of constant radii. These have slope minus 4, and the small radii are on the left bottom corner, and the big stars are on the right upper corner. So these are the dwarfs, small stars, and there are the giants on the other side. So this is how these two parameters are displayed. The mass, it's not that easy, but the Hertzsprung-Russell diagram is one way to represent stellar parameters. Well, there is actually a maximum to the luminosity, and we will see why. Let's consider the equation of radiative transport. Luminosity is proportional to the temperature gradient here in the Lagrangian scheme. Luminosity is minus diffusion coefficient times the temperature gradient in terms of mass. So taking the Lagrangian variable mr as the independent variable. Now I pointed already out that this factor t to 3 can be rewritten in terms of either the radiation energy density or the radiation pressure. Radiation pressure is given by P rad. P rad is proportional or is equal to a third times temperature to the fourth. So the a third times temperature cubed times the temperature gradient might be written in terms of the gradient of the radiation pressure. Even we can also take out one density, and we can transform from the mass as a Lagrangian variable to the radius as an Eulerian variable. Then we get a factor of 1 over 4 pi r squared rho, and we can rewrite this equation for radiation transport like the luminosity is given by this factor which contains as an important quantity these r squared and the opacity. Well, a gradient of a pressure is nothing else but a force per volume. Pressure is force per per area. So this is force per volume, and we can get an acceleration from that simply by multiplying it by 1 over the density. So 1 over the density times the gradient of the radiation pressure is something which is the acceleration caused, or the acceleration exerted on matter by the radiation pressure. So 1 over rho gradient of radiation pressure is the acceleration of matter coming from the radiation. So the radiative acceleration A rad is simply minus 1 over rho times the gradient of radiation pressure, and we read off from this equation that it's given by kappa over 4 pi c r squared times the luminosity. Now, there is not only the gradient of radiation pressure, which needs to balance gravity in an equilibrium situation. The total pressure gradient balances gravity. The total pressure gradient contains not only the radiation pressure gradient, but also the gradient of gas pressure. So for equilibrium, we need that the radiation pressure, that the radiative acceleration should be smaller than the gravity. If radiation pressure is already bigger than gravity, then in addition, the contribution from the gas pressure gradient will always exceed the gravity, so the maximum radiation pressure is gained once we have that the radiative acceleration is equal to gravity. This is the maximum which we can have, otherwise we will not find an equilibrium. Okay, agree? For equilibrium we need that this radiative acceleration should be smaller than the acceleration by gravity, which is given by gm over r squared. But keep in mind we have an additional acceleration by gas pressure gradient, so the maximum is really given once the radiative acceleration is small, it has to be smaller than the gravity. So if we insert this now here for radiative acceleration and the gravity, well, both scale with 1 over r squared, so the 1 over r squared cancels, and we are left with a condition from here that the luminosity has to be smaller than some constants involving speed of light, gravitational constant, and the mass divided by the opacity. So two factors matter for this maximum luminosity. It's the mass and it is the opacity. This luminosity, which is given by this expression, is called the Eddington luminosity, which is the maximum luminosity of any object that is kept in equilibrium by gravity. So they cannot have a bigger luminosity than this value, otherwise the radiative acceleration would become bigger than the gravity, and there is no equilibrium possible anymore. We are talking about equilibrium. Sometimes people confuse it with stability. We have nothing said about stability. It's a condition for the existence of an equilibrium. So if we don't match this condition, we cannot even have a stationary or a configuration in equilibrium, irrespective of the stability or instability of the object. So this is not a stability criterion. It's a condition for the existence of an equilibrium at all. Okay, so Eddington luminosity is the maximum luminosity for some equilibrium or static configuration with mass m. How big is it? The question, so we just have to insert this a typical value for the opacity and the mass for the sun, for instance, then on scale or express the mass in units of the solar mass. Then we have The Eddington luminosity is around 10 to 4 solar luminosities times the mass over the mass of the sun. So there is an important limit for the luminosity, which is the Eddington luminosity. Actually, once we consider pulsating stars, some of them are pretty close to the Eddington limit, so they are still in equilibrium, but they might be stable or unstable. Stability is a completely different concept from equilibrium. For stability, we have to have first an object which might be unstable or stable, which has to be in equilibrium. So the first condition would be we have an object below the Eddington limit where we can construct a stationary equilibrium configuration, and then afterwards we may ask the question, is this object stable or not? So don't confuse the concept of equilibrium, existence of equilibrium, with the concept of stability or instability. Okay, that's what I wanted to say about the stellar parameters. Well, the next issue would be the equation of state. Okay, this is an important point or an important quantity, an important issue to close the system of our equations. Well, stellar matter, that's taken from the observations. If we observe a star, we observe that it has a chemical composition. We can deduce it from the spectral lines we observe. So we see that stellar matters, once we look at the spectrum, contains a mixture of various nuclei, atoms, ionized atoms, electrons, and of course, because we see the star, a lot of radiation. The temperatures and densities which we deduce from the observations, the sun, for instance, has a photospheric temperature of around 5000 K. The temperature will increase inside because pressure and gravity should be in equilibrium, and therefore the pressure must increase inward, and therefore also the temperature. So the photospheric temperatures are the minimum temperatures. The temperatures will increase towards the center. And if we compare then, if we look at the densities, the mean density of the sun is remarkably low. Does anybody know what is the mean density, roughly order of magnitude of the sun? Yes, it's close to 1 gram per cubic centimeter. So it's pretty low density. And if you consider temperatures and densities gained from observations, then you would say, or you would conclude that it's the stellar matter has the aggregate state of a gas. It can be described by the equation of state of a gas in the ideal case, or in the case when the densities are very low and temperatures are high enough. That means we can describe the particles, the atoms, nuclei, ionized atoms and electrons simply by an ideal gas. And the equation of an ideal gas is given by gas pressure is proportional to the temperature and is proportional to the density of the star. And to account for the chemical composition, we have here the mean molecular weight, and the mean molecular weight should include the chemical composition, different chemical composition, but it also includes the physics of ionization. So the mu has to be determined in a very complicated way by considering the ionization states of different atoms, whether we have ionization, to which degree. It has to include the various energy levels within an atom. So it's a rather complicated way to determine the mean molecular weight, taking into account all the ionization processes, and this mu itself depends on chemical composition, depends on the density, depends on the temperature, and it requires a lot of atomic physics and atomic calculations to get out the mu as a function of density and temperature. So keep in mind, well, it's not that simple in the outer layers of the star where we have ionization processes, incomplete ionizations in the star. This mu depends sensitively on temperature and density and on the chemical composition. So mu itself is a function of rho and t. Okay, and then this is a description of matter within our star and the description of radiation, the pressure of radiation. It's much simpler. Radiation pressure depends only on the temperature, and we already wrote it down. Radiation pressure is radiation constant over 3 times temperature to the 4. So for normal stellar matter, for ordinary stellar model, the total pressure, the equation of state for the matter is given by the sum of gas pressure plus radiation pressure. It's usually written down in the form gas constant over mean molecular weight times density times temperature. That's the gas pressure plus radiation pressure. This is A over 3 times T to the 4th. Once we have the pressure as a function of density and temperature, or you can also take pressure as a function of density and entropy, or temperature and entropy, we also have a caloric equation of state, which tells you the dependence of the specific internal energy on temperature and density. Well, the specific internal energy for the gas is 3/2. This comes from the 3 degrees of freedom. Each degree of freedom gives you 1/2 kT. And so this is the 3 translational degrees of freedom. 3/2 R over mu. If you compare it to the pressure, it's a very, very similar relation. So pressure is R over mu rho T. So this is 3/2 R over mu times T. And for the radiation pressure, we have that the energy density goes with A times T to the 4th over rho, because we have the specific internal energy U here, plus, of course, any energy density is only determined up to a constant. So these are the 2 equations of state we usually have for the matter, the thermal equation of state and the caloric equation of state. Once we have these 2, then we can play around with the thermodynamics, and we can derive from these 2 any other quantity we want to determine, which is, for instance, the entropy. If we have pressure and internal energy, we can calculate the specific entropy. We can calculate some of the coefficients which we need for stellar evolution, which is the specific heat at constant pressure. These are the coefficients, the logarithmic derivatives occurring as coefficients in the equation of state. So this is d log rho by d log p at constant temperature. This is d log rho by d log t at constant pressure with a minus sign. We also have quantities like this, nabla adiabatic. This is defined as d log p by d log t at constant entropy. This definition of nabla adiabatic, this is determined by the equation of state. Without any reference to a particular stellar model, nabla adiabatic is simply a quantity to be determined from thermodynamics of the matter. So this can be deduced directly by means of standard thermodynamic relations. Okay, I wanted to say something else. Okay, I forgot. Well, this equation of state is valid as long as the temperature is high or comparatively high, and the densities are low. Okay, so what happens if we go to low temperature, and the question is then whether these conditions appear also or are also present in a star. What happens if temperatures are moderate, or for terrestrial standards it might be even high, but if the density becomes high? Well, for this purpose, let's consider the pressure of electrons. Let's consider the situation that the stellar matter is completely ionized and that the electrons contribute significantly to the gas pressure in that sense. So they make up a significant contribution to the pressure. What happens to them at low temperatures? Well, if the temperature for an electron becomes low enough, then we have to take into account that electrons need to be described by Fermi-Dirac statistics. That means they are quantum mechanical particles with half integer spin. So electrons have half integer spin, and they are therefore fermions. They are not bosons, are those particles which have integer spins. So electrons are fermions which have half integer spins, with the consequence that in a quantum mechanical state we can get only two electrons, one with spin up and one with spin down. Or in other words, they have to be different in at least one quantum number. The quantum number would then be the spin. So, okay, so if we construct the possible states, the possible quantum mechanical states for the electrons, we can put into one state at maximum two electrons, spin up, spin down. Well, what is the potential in which our electrons move? Well, our star acts as a box. The electrons are contained in a box, and the box is provided by our star, a box or a potential pot. So the zeroth approximation would be we have a potential pot with infinite potential on the walls and zero potential in the middle. So we have to fill into our potential, we have to fill in our electrons. So for this potential pot, we have a fundamental state, a state with lowest energy, which is not zero. That's a quantum mechanical effect. There is the lowest energy state, and then we have a sequence of state. And once the temperature is low enough, then all these states are filled up to a maximum energy. If the temperature is high enough, of course, they can escape here and can take other states or can become unbound to the system. But if the temperature is low enough, then they have to be filled in the potential pot of our star and have consecutively fill all these states up to a maximum energy. When we have put in all electrons, then we arrive at a maximum energy E0, or equivalently at a momentum P0. Energy E0 corresponds to the maximum momentum. Okay, that has to be done. Once we go to very low temperature, we have to take into account that these are fermions and they have to obey Fermi-Dirac statistics. Okay, for T going to 0, all states are occupied up to maximum energy corresponding to maximum momentum P0. And this effect is known as, or is called, degeneracy. So the electron gas becomes degenerate, and this means it fills all possible states, all the available states, up to a maximum energy and a maximum momentum, which depends on the number of electrons we have to fit in. So if the maximum energy is defined by the number of electrons which we have to put in our potential pot. Okay, what does it mean? Well, number density is, well, now we would like to take this picture and we would like to know the number density, or the relation between the number density, the maximum energy, or the maximum momentum of our electron distribution. Well, the numbers of electrons will be proportional to the space available to the phase space available to the electrons. This is nothing but the number of states here we have in energy to fill. Well, this will be proportional to the phase space in energy or to the phase space in momentum. So it's simply proportional to the volume of phase space which are accessible to our electrons. The number density of electrons will be the integral over the phase space. This is the phase space volume in spherical coordinates. So we take the phase space in 3 dimensions and take a spherical distribution. There is no position in phase space is special. So there is it's simply the volume of phase space integrated from 0 to the maximum momentum. Well, this integral is easily calculated. This goes with P naught cubed. So the number of electrons per volume which we can fit in is proportional to the maximum momentum of the distribution in our potential pot. The energy density then is simply given by writing the energy per particle here and also integrating over the momentum or the phase space. So the energy density of our particles is the integral over the phase space times the energy of a single particle, also taken from 0 to the maximum momentum. Okay? Well, now we have to distinguish between between the properties of the particles and the relation between the energy and the momentum of the particle. If the particle is a classical particle, a non-relativistic particle, then we have that epsilon is the kinetic energy of a particle is given by the momentum squared over 2m. Is this known to everybody? The kinetic energy is given by momentum squared over 2m. So we have to insert this here, but that's not always true. For very fast particles, which are relativistic, the epsilon is a linear epsilon, and the momentum is a linear relation. Then epsilon is given by speed of light times the momentum, and in that case, we have a different relation between the energy and the momentum. So this integral will be different once we consider non-relativistic or relativistic particles. So the energy density goes with integral over p to the 4th for the non-relativistic particles, or goes with p to the integral over p to 3 for the relativistic particles, and that means that the energy density goes with maximum momentum to the power 5 for non-relativistic particles, and goes with the maximum momentum to the 4th power for the relativistic particles. Okay, now we have 3 relations. We have that the number density goes with maximum momentum to the 3rd power. The energy density goes either with a power 5 or power 4, depending on whether our particles are relativistic or non-relativistic. And now we can construct from that a relation between the electron pressure and the density in the following way. The electron pressure is proportional to the energy density with a factor 2/3 for non-relativistic particles and with a factor 1/3 for relativistic particles. Actually, in the following, these 2 factors will not matter. It's the dependence on the maximum momentum which will matter in a second. So this goes, pressure of the electron goes with the maximum momentum to the 5th power, non-relativistic case, and with the 4th power in the relativistic case. Now we know that the maximum momentum is related to the number density of particles. Number density goes with the third power of the maximum momentum. So we express the maximum momentum in terms of the energy density. Maximum momentum goes with the 1/3 power of the number density. So we have, in the end, that the pressure goes with the number density of the electrons to 5/3 in non-relativistic case, and with the power 4/3 in the relativistic case. If we have charge neutrality, then the number density of the electron will be proportional to the mass density of the nucleons. So this will be then of the order of the number density of the electron will be proportional to the density, and the same also for the relativistic case. So we have that the electron pressure will go with the density to 5/3 non-relativistic, and will go with the power of the density to 4/3 in the relativistic case. What we see here, it's obvious, of course, from the construction, the temperature does not enter this relation. So we have an equation of state relating pressure and density only. Temperature has been dropped. Temperature is no longer a parameter, and this is another expression of degeneracy. Yes.
How we got that 2/3 and 1/3?
Well, this I haven't proven that. This is a general relation. You, if you are interested, I would ask you to go to thermodynamics, where the relation between pressure and energy density is calculated for relativistic and non-relativistic particles. Anyway, this fact, it's given just for completeness. These factors do not matter for our purposes. It's I have added it just for completeness. I'm sorry, I didn't go into further. Otherwise, I would have to present a complete lecture on thermodynamics. I'm sorry about it. But it doesn't matter. If I would have left it, you get the same result. Okay. Well, let's go further on. Well, the question is, what is the condition for temperature to be small? Well, temperature to be small, we have said, well, for low temperatures, this means we have to specify what we mean by low temperature. It means that the thermal energy, the usual thermal energy of an ideal gas, where the thermal energy of a particle is of the order kT. If this is small compared to the maximum energy once we have complete degeneracy, then we say the condition of degeneracy is satisfied. So in order to see the effect of degeneracy, this means that the maximum energy in the degenerate case of degeneracy, it has to be much smaller, much bigger than the thermal energy. This is the condition for degeneracy. Well, and taking the case that the particles are described by classical particles, non-relativistic particles, this maximum energy is related to the maximum momentum by p0 squared over 2m, and m is the mass of the particle. Now if we insert again the relation between maximum momentum and the number density, so kT has to be smaller than 1 over m, the mass of the particle, times the density of our electrons to 2/3. This relation actually is valid for all fermions, and so what you see or deduce from this relation here is that the onset or that the degeneracy comes later for more massive particles. The degeneracy condition is satisfied for more massive particles later than for the small, less massive particles. So the particles, the lightest particles we have in our stellar mixture are the electrons. So the first ones who will degenerate are the electrons, and the nuclei still are non-degenerate because they are at least 1,000 times more massive than the electrons. So we have in our mixture, once the degeneracy sets in, degenerate electrons and non-degenerate thermal nuclei. That's why we have to deal with the degeneracy of electrons first. The degeneracy of nuclei comes much later. Okay, the nuclei degenerate later than the electrons at lower T, and in the degenerate situation, the degeneracy pressure will always be much bigger than the thermal pressure. So in that case, once we have a mixture of non-degenerate and degenerate particles, always the degenerate particles will be responsible for the pressure and the other particles will become negligible. So the nuclei will be negligible concerning the pressure compared to the electron pressure once the electrons degenerate, once the electrons becomes degenerate. So for degeneracy, electrons, yeah.
Working in the units C equal to 1 and Z equal to 1.
Naturally.
Pardon? C equals G equal, no. I have dropped all the constants here. It's just the relation. Well, all constants have been dropped. Only those quantities which are interesting have been kept. So that, of course, you have to, in order to get the dimensions right, you have to add some of the constants C and whatever. For clarification, I only took those quantities which are important physically. Okay, another consequence of that is once we want to keep the degree of degeneracy, well, we can take this ratio, temperature to the density to 2/3 constant. We can take the ratio of kT and the P0 squared over 2m as an indication for degeneracy or as a degree of degeneracy. Once we would like to keep this ratio of thermal energy and degeneracy energy constant, then we see here that then the temperature would have to go with the density to 2/3. Only then we have a constant degree of degeneracy. So if we want to keep the degeneracy constant, this will become more important later. Then the temperature has to increase with the density, at least with a temperature with the density to 2/3. If it decreases more with a lower exponent, then the degree of degeneracy will increase. If the exponent is bigger, then it leaves the degeneracy and becomes less degenerate. Okay, well, again, to summarize, degeneracy means the equation of state becomes independent of the temperature. So if the temperature is low enough, then we have that the pressure is equal to the electron pressure. The electron pressure then only depends on density, and therefore the pressure only depends on density because the pressure of the non-degenerate particles becomes unimportant. And we have to distinguish between non-relativistic electrons and relativistic electrons. For the non-relativistic electrons, we have pressure proportional to rho to 5/3, and for the relativistic ones, we have pressure proportional to the density to 4/3. By the way, how big is alpha and delta for these guys? D log rho by d, the alphas and deltas are defined by an equation of state of that form, rho of P and T. Well, the dependence on temperature is dropped. So what is delta here? Delta was d log rho by d log T at constant pressure. It's 0, so delta is 0 for a degenerate gas, and alpha is equal to d log rho p, it's the inverse. So d log rho by d log p is 3/5, or it's 3/4 for the relativistic electrons. So this, you see, this is one case where you can apply this definition of alphas and delta. By the way, what is alpha and delta for an ideal gas? P is P equal to rho times T, or rho is P over T. Log rho is log P minus log T. So alpha and delta is unity. Alpha is equal to delta is equal to 1. Okay, just as a small by remark. Okay, well, the question is degeneracy such a remarkable effect which occurs only in strange astrophysical situations? I will promise you it occurs. Some stars are living from this degeneracy effect. Or do we observe degenerate electrons also on Earth? Do we see degenerate electrons on Earth? Well, think of everyday life. Is there someone who is familiar with solid state physics, with metals? Electron in metals are degenerate. They suffer from the same degeneracy as the electrons in a star at low temperatures. So degeneracy is nothing very uncommon. It happens in a metal. It's normal for metals. Okay, so I have now, unfortunately, it's a diagram in German. Well, the various domains where the different equations of states are valid is given here in a temperature density diagram. So we have log rho here, the density we have as a function of log rho and log t, the various ranges where the various equations of state are valid. So at very low densities, very high temperatures, we have radiation pressure. So low temperatures, low densities, and high temperatures mean we have a normal, so-called normal equation of state, and low densities means the gas pressure becomes unimportant. High temperature, the temperature to the four terms will dominate. So this is radiation pressure. If we decrease the temperature, increase the density a bit more, then we end up with an ideal gas. So then the radiation pressure is no longer dominant, but the gas pressure being proportional to rho times T will become important. Once we decrease temperature even more and increase the density, we enter the domain of degeneracy. First, the non-relativistic degeneracy with alpha equals 3/5, delta equals 0. And if we increase the density even more, then we enter the domain of relativistic degeneracy with delta equal to 0 and alpha equals to 3/4. Ideal gas, again, alpha and delta are equal 1. Okay, that's what I wanted to say about the equation of state, and we will see the consequences for stellar structure and evolution later on, because there are stars which are governed by an equation of state which is given by the degenerate electron gas, and they have special properties, and we will study them on the basis of what we saw for the equation of state. P going proportional to 5/3 and P going proportional to 4/3 in the case of relativistic or non-relativistic degeneracy. Any questions? about that? Well, this actually one would have to go through the entire quantum mechanics to do this really in detail. I try to pick the most important parts and the most important connections here without reference to the complete thermodynamics. So there are of course some gaps here which I have to leave, but otherwise this would be a lecture on itself. Okay. Okay, so next quantity which we need to consider is the opacity. Well, the opacity describes the interaction of photons with matter. Absorption, scattering, any re-emission of photons by atoms, this is all described by the opacity. So in general, the interaction of photons with matter is described by the opacity. There's one source of opacity which is always present, which is very simple to describe. This is the scattering of photons at electrons. So if we have an ionized material, then we have sufficient electrons available. This happens inside the star. Deep inside the star, everything is ionized. We have free electrons, and the photons collide with the electrons. This is particularly efficient because they are the less massive particles, and therefore the scattering of the interactions with the electrons is the most important process. Well, this is called Thomson scattering. Electron scattering is Thomson scattering of photons at electrons, and well, I don't derive this in detail. You have to you have to go to quantum mechanics, quantum electrodynamics, to derive the cross section of the interaction of a photon with an electron. The result is pretty simple. It has a constant cross section. It does not depend on density and temperature. It's simply constant, and it's given by elementary constants. So it depends on the elementary charge, on the mass of the electron, and on the speed of light. These are the only dependencies. So it's a constant given only by fundamental constants. So what you have then as the opacity, once this is the cross section, the opacity is then given by this constant cross sections times the number density of the electrons divided by the density. Number density of electrons in the case of a fully ionized gas is essentially constant. So the number density of the electrons over the density is then given by the mass fraction of the hydrogen only, which accounts for, well, usually we have in a symmetric nuclear metal, we have 1 neutron per proton. This is not true for hydrogen, and therefore the hydrogen mass fraction occurs here. But so the opacity depends a little bit on the hydrogen mass fraction. It's given by 0.2 centimeters squared per gram times 1 plus x, because the proton, of course, that disturbs the symmetry of nuclear metal. We have then more protons than neutrons, and therefore the mass fraction of hydrogen comes in here. So this assumes fully ionized matter. So this is one source of opacity, and it's simply a constant. Of course, once we don't have electrons, for instance, if the matter is cool and we have recombination and the electrons disappear, then this source of opacity goes away. Okay, the next is the free transitions. What is that? Free transition. This means that an electron passes a nucleus or passes an atom, but it does not get bound. It just travels along on a hyperbolic orbit. That means it goes from a free state of an atom to a free state afterwards. free transitions. More important and more important are the bound-free transitions. These are the ionization or recombination processes. So a photon hits an atom and it removes an electron from the atom, which comes into a free state. The opposite would be the recombination. These processes take out a lot of energy, and these contribute to the opacity in a very efficient way. These are the bound-free transitions. So photoionization, keep in mind, is one of the processes which contribute to the interaction of photons and matter and lead to a significant contribution to opacity. The next processes are the bound-bound transitions, which have for a long time been ignored or largely ignored. Now I've again problems with the okay, thanks. Bound-bound transition. This is an interaction with photons of atoms where an electron is put to a higher state, but it is still bound. So you have various levels within your atom. You take out, for instance, at the inner shell, you take out an electron and it's put on a higher energy level, but it does not get photoionized. So this does not lead to an ionization of the atom, but it still gets the atom into a higher energy state. These are the bound-bound transitions, and we will see an example for that later on. Then there is a process which is important for low temperatures in stars, which is the so-called H- opacity. It is the process that a hydrogen atom, a neutral hydrogen atom, catches an electron, provides or goes to an H- ion. This is an equilibrium reaction, so it can go both ways, but it consumes energy from the radiation field, and in this way it can contribute to the opacity. So this process also contributes to opacity, but it's significant only at very low temperatures. And of course I have to, for completeness, I have to add here the conduction. If the electrons become degenerate, then the conduction is a process, or it contributes, heat conduction contributes to the energy transport, and this conduction is usually or is done by the electrons, because then they have the biggest mean free path, and then they contribute, so to say, to the opacity. You can include conduction formally in the opacity, and this is done if electrons become degenerate, but we will not consider this here in detail anymore. Well, the opacity strongly depends on chemical composition, because of course these bound transitions will depend on which atom we have. Also the free transitions will depend on which particular atom we have. So if we have a hydrogen atom or if we have an iron atom, this will very much influence these transitions and therefore very much influence the opacity. So keep in mind, opacity strongly depends on chemical composition, and to calculate the opacity, it's again a very hard task for atomic physicists, and there are nice guys who provide tables depending or with parameters chemical composition, provide for different chemical compositions as a function of temperature and density or pressure and density, provide the values of the opacity. So for realistic calculations, there are nice guys who have provided the opacity tables. There are essentially 3 projects. Well, one of them is sponsored by Los Alamos Laboratories. These are the LAOL opacities. The other one are sponsored by Livermore Laboratories. These are the OPAL opacities. And there is a project, OP project, which is done by MHD, which does not mean magnetohydrodynamics. This is Mihalas, Hammer, and Deppen, three guys who thought they would like to provide opacity tables for their honorary astronomical colleagues. So there are groups which deal only with the calculation of opacity tables. This is a non-military military project. The other ones are somehow connected to military. Of course, you see this with the address Los Alamos and Livermore. Actually, the first opacity data came from experiments with the atomic bombs. So the first hints. So that's why these guys are interested for other reasons also in opacities, and in their free time they calculate opacity for their astronomical colleagues. Okay. So the parameters of these tables usually density, temperature, or alternatively pressure and temperature and chemical composition. Do we have to stop here? Okay, just one result. Okay, so what one gets here is here again the range. Again, this is again a log rho log t diagram. Now different values of the densities and temperatures as compared to the equation of state. And here you see for high temperatures and low density, the dominant source of opacity is the electron scattering. Once we decrease temperature, increase pressure, then we have the photoionization processes, bound-free and bound-bound transitions. There is a small range where we have three free transitions, and at very low densities and very low temperatures and high densities, then we have conduction by degenerate electrons. So for a wide range of parameters, electron scattering and the bound-free and bound-bound transitions are the important sources for opacity. Let me show a next diagram. Well, once we cut through this diagram and plot the opacity as a function of temperature, keeping, for instance, the density constant, we see that the kappa has typically, the opacity has typically 3 maxima, and for high temperatures it goes to value around 0 point something. So the question is, what causes the level here at high temperatures of, say, around a little bit below 1 centimeter squared per gram? High temperatures, everything is ionized. Everything is ionized means also all atoms are ionized. So we cannot have bound-bound or bound-free transitions because all electrons are gone. We just have the nucleus. So what is left, but what is always left if one? It's which source of opacity is left at very high temperature? Electron scattering. So it levels off at the value of electron scattering, and if we go to moderate or low temperatures, then we observe these 3 peaks. I have to tell a small story. This dotted line is based on an opacity table which was available until the 1990s. And this shows the 2 peaks here, but it doesn't show that one. And in the 1990s, some clever guys at Los Alamos and Livermore, they have sit down and saw we missed so far a source of opacity, and this source of opacity provides this new peak. And so all stellar evolution calculations essentially had to be redone because this peak was missing so far. And it is also very important for pulsations, because each of this peak can be responsible for or an instability of stars for exciting stellar pulsations. Well, we'll talk about or interpret this diagram tomorrow then. So, but just for thinking about until tomorrow, consider this diagram. We will comment on that tomorrow more. Okay, thanks for the day.